In this video, we're going to be talking about blocks. So first, before we get to blocks, we need a couple of other definitions. A non-trivial graph that has no cut vertices is called non-separable. Okay, so remember we've talked before about what cut vertices are. So if it doesn't have any cut vertices, then it's called non-separable. And it turns out that it's sort of easy to see when a graph is non-separable because of this theorem. A graph of order at least 3 is non-separable if and only if every 2 vertices lie on a common cycle. So let's see what this looks like. So let's consider this graph here, which has a cut vertex, right? So, whoops. So V is a cut vertex as opposed to this graph, which has no cut vertices. So this graph is non-separable. This graph isn't. You might say it's separable. So what does this mean, every 2 vertices lie on a common cycle? Well, for example, let's just say I take this vertex U and this vertex V. Well, I can find a cycle that has both the vertices U and V on it. So let's see. So I'll take this edge and this edge and this edge and this one and this one and this one. Right? So there's a cycle that has U and V, and you can do that for any 2 vertices. As opposed to in this graph, let's say I take these vertices, X and Y, there's no cycle that uses both X and Y. So that's what this theorem says, is if you can find a pair of vertices like this, then you know there has to be a cut vertex, and if you can't find a pair of vertices, then there isn't a cut vertex. Okay, so that's kind of nice. Now let's talk about a block. A block in a graph is a maximal non-separable subgraph of G. Okay, maximal meaning it's the biggest it can be, but that's a local condition, right? It's not maximum, maximal, there's a difference. Non-separable meaning there are no cut vertices, and it's a subgraph meaning you can delete vertices and edges from the original and get down to it. So let's see what this actually looks like, considering this graph in yellow here. So we want maximal non-separable subgraphs. So let's start with over here. Let's consider this, say, this little triangle here in the bottom left corner. Let's start with that. Okay, so this is a subgraph, right, of our original. And it is non-separable. There are no cut vertices. But is it maximal? It's not, because I could also add in this piece. This is also a subgraph. It's also non-separable. And now, right, this is bigger. It contains the one before it. And it turns out that this one is maximal, because as soon as I grab anything from over here in this part of the graph, now I'm on the other side of a cut vertex. So these cut vertices sort of represent bottlenecks in the graph, if you want to think about it that way. And so a block is sort of saying, okay, well, here's all of this piece on the left on this side of the bottleneck, and I'm separating that off from everything else over here on the right. So this is one of the blocks. Similarly, one of the blocks will look like this. And now, do we or do we not include this edge? We do, because we want it to be maximal. Okay, so this is a block. Again, it's a subgraph. It's non-separable. And if you add anything else, see, this is a cut vertex and this is a cut vertex. If you add anything on the other side of a cut vertex, you're not going to keep your non-separability, right? Because then you'll have, that vertex will be a cut vertex. So in this, for example, this was a cut vertex in the original, right? But it's not a cut vertex here because there's nothing on the other side. And similarly, this and this were cut vertices in the original, but they're not here because there's nothing on the other side. And then this also has another block, right? This single edge here. So essentially a block is what you get when you peel the graph apart at the cut vertices. And formally, that means what you're doing is you're taking maximal, non-separable subgraphs. Okay, so now a theorem about this. So let R be the relation. Remember, we learned what an equivalence relation was not so long ago. Let R be in a relation defined on the edge set of a non-trivial graph by the edge E is related to the edge F if they're the same edge, or if E and F lie on a common cycle of G, and then this just says where E and F are edges of G. Then this is an equivalence relation. Moreover, the equivalence classes are what? Well, given the title of this video, it should be no surprise that the equivalence classes here are blocks of G. So let's see what we're talking about here. So remember, an equivalence relation satisfies three things. It's reflexive, symmetric, and transitive. So you may want to go back and review that if you don't remember that. But let's just consider what's happening here. So based on our discussion above, we should be able to just recognize immediately what the blocks are, right? Ignoring the theorem above. The blocks are where you peel across the cut vertices, right? So for instance, this is a block, and this is a block, right? Here's our cut vertex, and we're just sort of peeling it apart. But now what this says is, this theorem says that if you consider an equivalence relation where two edges are related, if they're exactly the same, or if they lie on a common cycle, then, for example, 1 is related to 2, right? Because 1, 2, and 3 are on this common cycle. Similarly, 1 is related to 3, 2 is related to 3, right? And because it's symmetric, that means 2 is also related to 1, 3 is also related to 1, 3 is also related to 2. So this is an equivalence class, right? Like 1, 2, 3 is going to be an equivalence class because, right, you can see that if you take 4, for example, there's not going to be any cycle that has both 2 and 4, right, in common. So remember, the relationship above says that edges are related if they lie on a common cycle, but for instance, 2 and 4 won't, 1 and 4 won't, 4 and 3 won't, and the reason is because they're on opposite sides of a cut vertex. So what this relation does is it sort of divides up the edges, right, on either side of a cut vertex, which is exactly what it means to be a block. So for example, our equivalence classes over here will be 1, 2, 3, and then the other one will be 4, 5, 6, 7, and 8, right? Because 4 and 5 are related, 4 and 6 are related, 4 and 7 are related, because you can imagine this sort of cycle all along the outside here, right? So all of those are related, but then you can say that 4, 5, and 8 are related, and 4, 7, and 8 are related, and because of symmetry and transitivity, that means that each one of these things is related to each other. So you get these two equivalence classes, right? 1, 2, and each of those corresponds to a block in the graph. So that's what this theorem says. If you consider the equivalence relation where two edges are related if they lie on a common cycle or if they're exactly the same, then that means this is in fact an equivalence relation, and it divides your graph up into blocks. Okay, so that's our introduction to blocks.